Everybody, Doc here. We're going to start chapter 2. This is going to be a shorter lesson today. We have a short class. So let's get moving forward and learn about some functions. We're going to look at what is a function. We're going to find their functions all around us, the definition of a function. We're going to learn how to evaluate a function, the domain, and 4 ways how to represent. So in nearly every physical phenomenon, we will observe some quantity that depends on another. So for instance, how old you are depends on your height. And we can argue to a certain point, then you stay a certain height for a certain while. But anyway, just understand that we know that a 2-year-old is generally not going to be as tall as a 20-year-old. Temperature is a function of the date depending on where you live. Temperature is determined. Right now we are in southwestern Pennsylvania and it's September 1st and it's a gorgeous day outside. And when we're in January, we'll be cold. I don't personally like the cold, you might, but anyway, that'll be a function of the date. And here we have a table that shows postage depending on weight of a package that is mailed. We use function to describe this dependence of one quantity on another. That's what we're saying. Height is a function of age. Temperature is a function of date. Cost of mailing a package is a function of weight. So some more examples would include the area of a circle that is a function of its radius. Number of bacteria in a culture is a function of time. The weight of an astronaut is a function of her elevation. And the price of a commodity is a function of the demand for that commodity. So a rule that describes how the area A of a circle depends on its radius r is given by A equals pi r squared. So even when a precise rule or formula describing a function is not available, we can still describe the function by a graph. For example, when you turn on a hot water faucet, the temperature depends on how long the water's been running. So we can say temperature of water from the faucet is a function of time. We'll take a look at the definition of function. A function is a rule. So to talk about a function, we need to give it a name. So we often use f, g, and h are the most popular ones. And so we will say f is the rule, the square of a number. So a function is a rule that begins to assign to each element in the set exactly one element called f of x, that's the result that you get in a set B. So this exactly one element is very important for you to remember in this definition. We usually consider functions for which the sets A and B are real numbers. Remember that when we're talking about sets, we're using uppercase letters. This symbol is read f of x, or some people read it f at x. Generally, I hear it more often as f of x. And it's called the value of f at x, or the image of x under f. The set A is called the domain. This is everything that you can put into that function to get a result. And the range is the set of all possible results that you can get when you put your domain into a function. Now we can look really fancy when we're writing our answers because we can start using these symbols. And this is read as f of x. Actually, I should start from the very beginning, so I'll start over here. So the range of x is equal to f of x such that x is an element of A. So, some important symbols to remember. This right here is such that. Until I haven't done this in a couple days, it's getting bad again. So that's such that. So you want to remember that symbol. Whew, a little bit crazy. Okay, and then this symbol right here means element of. And depending on where you went to school, it probably depends on whether they taught you these symbols or if they just skipped that part. But now it's time where you really need to recognize that, boy, my writing is terrible. My 4-year-old grandson could do better than this. Okay, so element of, actually not elements. Let me get rid of the there. Element of. Okay. The symbol that represents an arbitrary number in the domain of a function is called an independent variable. So that's the variable that you are putting that is independent to the function. Now the symbol that represents the number in the range of f is called the dependent variable because it depends on what you put into the function. So your domain is independent. Your range is dependent. So again, domain, independent. Range, dependent. So if we write y equals f of x, then x is the independent variable and y is the dependent variable. So some people like to look at it as a machine. So here you have your input or your domain, and you put it into some kind of machine and you do something with it, and then out comes your product, and that's your output. So your domain is your input, your range is your output. So domain, input, and your range is your output. And sometimes we like to look at all the possible values as an arrow diagram. We put all of our independent values here, all of our dependent values here. So again, this is my domain over here, and this is my range over here. Actually, it looks too much like a real number symbol, huh? So we'll just put R. Okay, so each arrow connects to an element of A to an element of B. The arrow indicates that f of x is associated with x, f of A is associated with A, and so on. So a function is defined by a formula. Here we have it. We have this f of x equals x squared plus 4. Express in words how f acts on the input to produce the output. Evaluate f of 3, f of negative 2, and f of square root of 5. Find the domain and the range, and then draw a machine diagram for f. So the formula first tells us that f squares the input x and then add 4 to the result. So the action would be square, then add 4. The values of f are found by substituting for x in the formula. So you can see here, if I'm looking at f of 3, I'm going to put 3 in for x, and I get 3 squared plus 4, which is 13. F of negative 2, I'm going to put negative 2 in for x. So I get negative 2 quantity squared, that's positive 4, plus 4 is 8. And here I have f of square root of 5. So I'm going to square that, plus 4 equals 9. So domain consists of all the possible inputs. And since we are looking at this as a polynomial, there's no fractional exponents, there's no rational expressions, we know that all real numbers can work for this function. The range consists of all possible outputs. Now, for those of you that have done a lot of graphing with quadratics, you may be familiar with what this would look like. Okay, so for those of you that are not, we're actually going to be looking at that in this section, but for now, it is a parabola, and it's a parabola that goes up 1, 2, 3, 4. So it comes down like this, goes through here, and then goes back up. So we know that x squared always is going to be bigger than 0, because if you square a negative or a positive, it's always bigger than 0. And that means if we have plus 4 to that, we're going to raise everything up 4. So for the range is all y such that y is greater than or equal to 4. So this would be our range, and you might say, well, how do I know that? Well, this is exactly how. You need to learn what the parent function looks like and how it will be affected, and we will be looking at that in this chapter. Machine diagram would show all of your inputs over here, and then all of your outputs over here. Now, evaluating a function, this is where we pick numbers that will go into our function, and then we evaluate and get the answers. We did that in the last problem with a couple of them. Now we're going to look at this some more. So here is my function up here. And let's say, for instance, I want to check it at f of 1. I would put 1 here. So it would be 3 times 1 squared plus 1 minus 5. And if we did that, 1 squared is 1. So this would be 3 plus 1 minus 5. And if I go ahead and combine those, I'll get 4 minus 5, which is negative 1. Okay? So now they want you to look at negative 2, 0, 4, and 1/2. So let's take a look. So to evaluate f at a number, we substitute the number 4x in the definition. So I'm going to place negative 2 in for x, and then I place it everywhere where there was an x into the function. And this will become positive 4, so 3 times positive 4 will give me 12. 12 minus 2, because it's a negative, and then minus 5. So when I do that, I'll get 5. When I place 0 in for x, I'll have 3 times 0 squared plus 0 equals negative 5. Well, anything times 0 is 0, so this just cancels out, and then I'm only going to have negative 5 remaining. When I substitute in 4, okay, I have 3 times 4 squared plus 4 minus 5. 4 squared is 16. Always do your exponents first, follow your order of operations. Then multiply. 3 times 16 is 48. So I have 48 plus 4 minus 5. $52 minus 5 is 47. If I substitute in 1/2, same thing. Now remember, when you square 1/2, you're squaring the top and bottom. So this becomes 3 times 1/4. I'm going to try to put my numbers a little higher since I kind of ran into it last time. And then plus 1/2 minus 5. Well, 3 times 1/4 is just 3/4. So this will give me 3/4. And if I want to take a look at a common denominator, here I have 2/4. So that'll give me 5/4 for the first two. So I have 5/4 minus 5. Well, how do I write 5 with a denominator of 4? Well, I would put 20 over 4. That would equal 5, right? So now I have 5 minus 20, so that will be negative 15 over 4, not 5. I get ahead of myself. Okay, so over 4. Okay, so this will be negative 15 over 4. There we go, negative 15/4. All right, domain. Now again, domain are the set of all possible values of a function. Domain of a function is a set of all inputs for the function. The domain of a function can be stated explicitly. For example, we can write x is, now remember when you read these, you read from inside out, x is greater than or equal to 0, and x is less than or equal to 5. Then the domain is a set of all real numbers x for which x is greater than or equal to 0 or x is less than 5. Now, this doesn't mean that we're saying if I take this, that's the entire domain. This is saying that we are telling you that we are only going to use 0 to 5. Now, if we have an algebraic expression, we might have to consider the top and the bottom because we know that there are places in a fraction where you cannot have 0, can't have 0 in the bottom of a fraction. And we also know that in the square root, if we're looking at all real numbers, we cannot have negative values. So if I look over here at this first one, I see x minus 4. Well, where would that give me 0? That will give me 0 if x is 4. So x cannot equal 4. So that's where I will write it. It's all x such that x is not equal 4. Pick any other number than 4 and it'll work. Now here, I have to remember that the square root of 0 is 0, so 0 will work, but I can't have any negative. So I have to go x such that x is greater than or equal to 0. Find the domain of each function. So I take a look at this bottom, and I say, where is that going to be 0? Well, if I factored it, I'm going to have x times x minus 1 when I factor the bottom. Now when I look at that, I see I can't have 0 for x, and I can't have 1 for x. So not 0 and not 1. That symbol there means not equal to. I should have put 0 first because it's numeric order, but I didn't. Okay. Over here, I have to remember that I am subtracting something from 9. And I can't have anything that is negative. So the largest number I could have for x would be 3, because 3 squared is 9, and that'll give me 0. If I go bigger than that, I'm going to have a negative value under here. So I have to make sure that I have x smaller than or equal to, oh, not 9, I almost put 9, 3. Now, when I go over here and I look at the bottom, I have to remember that I cannot have 0 on the bottom. So where this would be 0 is at -1. So I know I can't have -1. And I can't have anything smaller than -1 because that would give me a negative value. So it has to be greater than, not greater than or equal to, because I can't have 0 on the bottom, but t has to be greater than -1. So let's see what they have for us. Okay, so rational expressions not defined when the denominator is 0. We said that. So we factor it. We see that we cannot have it being 0 or 1. So we would say x such that x cannot equal 0 and cannot equal 1. You could also write it in interval notation. So you could say from -infinity to 0, but not including 0, 0 to 1, but again, not including 0 or 1. That's why we have it in parentheses. And then from 1 to infinity, that would be interval notation. So if you have to write it in set notation, this is set notation. Okay. Set notation, and this is interval notation below that. Highlighter going a little crazy. Okay. All right, so in B, we can't take the square root of a negative number, so we have to remember that this has to be greater than or equal to 0. And we find out that as long as n plus or minus 3. So there was one that we didn't say plus or minus before. So plus or minus 3, because -3 squared is also 9. So we know that I can only have numbers that are between -3 and +3. So, and including those, since we have the equal to. So now I can write it in interval notation as -3 to 3. So again, we need to remember that we can square 3 in here, but we can also square -3 in there. We can't take the square root of a negative again, so this has to be greater than 0. It can't be 0 because it's on the bottom. So we have to say that for all t such that t is greater than -1, or we can write -1 to infinity, and actually should be parentheses here. I'm not sure why they did it that way. So interval notation would be -1 to infinity. Like this with parentheses, not with these. No, not with that. Just have it parentheses. Okay? All right, there are 4 ways to represent functions. We can address them verbally. We can address them algebraically. We can address them by looking at a graph, or we can address them by a table of values. If you take a single function, you can represent it in all 4 ways, and certain functions can be described more naturally by one method than another. So an example of a verbal description, if we're looking at temperature, we would say to find Fahrenheit equivalent to Celsius temperature, multiply the Celsius by 9/5 and then add 32. If we have the area of a circle as a function, we could say A of r, that's the radius, is equal to pi r squared. The graph produced by a seismograph is a visual representative of a vertical acceleration function of an earthquake. So with something like that, it's easier to look at a graph. And if you have a cost function, you may benefit from looking at a table instead. So cost of mailing a first class letter with the weight or in the table. Most convenient way of describing a function is numerically, and that's using the table values. So here again are the 4 ways to represent. You can represent it verbally, you can represent it by an expression, algebraic expression, you can have a graph, or you can have it in a table. And you might want to do all 4. So if you have f of c be the Fahrenheit temperature corresponding to Celsius temperature, f is a function that converts Celsius inputs into Fahrenheit outputs, the box above gives a verbal description of this function. So we're going to find ways to represent it. Let's represent it algebraically, numerically, and visually. So here is algebraically. Here's the equation. Those of you, I'm sure, had this in one of your science classes. At least I hope so. And we can put it in a table saying here's our input Celsius and our output of Fahrenheit. And we also may want to use a linear function. Notice that this is Celsius to Fahrenheit, and you'll see here that it starts at 32, and that's because that's our y-intercept. Okay, well that's all for 2-1. It is an introduction to chapter 2, and that's all we're going to do for this Thursday, so I will see you next time.